All right, so in this video, I'm going to cover 7.4.3 Bayesian uh, estimation. Okay. All right, so yeah, so let me cover the 7.4.3 by using my lecture note. Okay, so give me a second. Yeah, right here. Bayesian estimation of parameter. So, okay. Actually, Bayesian estimation. I mean, the Bayesian approach is the actually beyond of this subject. Okay, so Bayesian estimation is kind of can be considered as one individual the subject. Okay, this is really advanced and huge. So, but we're gonna see a little, see we'll just test a little bit of the Bayesian estimation, what it is. All right, so look at this. Statistical inference can be classified as two types: objective probability and then Bayesian approach. So objective probability is we're gonna uh, we know what we learned it, right? So we're gonna approximate the um, the population parameters based on the sample data, right? So all of the these what the doing I mean the finding point estimators based on the sample data that is called objective probability. But Bayesian approaches is different. So we're gonna use not only sample data but also other information. So what it is? So I mean that other information may be available prior to collecting the sample. So it's a little bit abstract. Let's see, but we can figure out that. So here's a question: how is this approach used in parameter estimation? Okay, let's answer. Suppose that the random variable x has a probability distribution that is a function of one parameter theta. Okay, so now we see that then what? The data is the population parameter. We can say that, right? So now then the PDF or PMF f can be denoted by like this: f of x bar theta, and the x is the what the random variable. And then this notation implies that the exact form of the distribution of x is conditional on the value assigned to theta. It makes sense, right? So think about the normal distribution. So PDF of normal distribution therefore depends on what the mu and the sigma square, right? You see, so depending on mu and sigma square, the PDF of normal distribution gonna return a different value, right? So now this second one, so suppose we have some additional information about, excuse me, about theta, and we can summarize that information in the form of probability distribution for theta. So then say f of theta. So now, yeah, here's an assumption. So we have some additional information about theta, okay? So that we can define the function of theta. It's actually PDF theta, right? So that is called the prior distribution for theta. Okay, so we can figure out the distribution of the theta, probability distribution of theta. Sorry. Okay, that is called the prior distribution. Now, and then we assume that the mean of the prior is mu zero and the sigma zero square. So keep in mind, this mu zero and sigma zero square is what? This is the mean of the prior distribution. Okay, so it means that what we're gonna consider theta as what random variable. Okay, and then next one, the probability associated with the prior distribution are called the subjective probability. So now this is so that is against to what objective probability, right? So we have studied objective probability. Now we're gonna study about the subjective probability. Okay, so the Bayesian approach to estimation uses the prior distribution for theta, f of theta, and the joint probability distribution of the sample, say x1 through xn, and then bar. There is a bar here, okay? Just, sorry for makes you confused, but this is bar. Okay, this is what conditional probability, right? But the since what theta is considered as a what random variable, okay? So I mean, means that this is nothing but what? This is function PDF of the sample data. I mean, observations x1 through xn, but theta is involved. Okay, so this is joint probability distribution of sample k minus. That is called the posterior distribution. Okay, sorry, not this is called the joint probability distribution of sample. Sorry, and then the objective, the goal of the Bayesian approach to find posterior distribution for theta, say f of theta bar x1 through xn. Okay, so now this is conditional probability of theta given the x1 through the xn, right? So okay, look at this. Keep in mind that. Okay. So now then, posterior distribution contains information from both the sample and the prior distribution for theta. Yes, that makes sense. Now then, joint the probability distribution of sample x1 through xn and parameter theta is what this. Now there is no part, right? So please look get the all three distribution carefully. Okay, this is what joint probability distribution of sample. There is a bar right there, and then posterior distribution, which is the goal in the Bayesian approach, f of theta bar x1 through xn, and then sample. I mean, joint probability distribution of sample and parameter. There is no bar. Okay, but this one can be expressed as what? Remember that the joint the formula of the conditional probability. This is that can be expressed as a conditional probability of f x1 through xn bar theta, but this is called what? Joint probability distribution of sample times what prior distribution f of theta. Can keep in mind this. Now it's okay. So yeah, it's too much abstract. Then look at this Bayesian search theory. This is one of the application of Bayesian approach. So Bayesian statistics has been applied many times to search for lost vessels at sea. So to begin, a map is divided into squares. See here the square right there. And each square is assigned a prior probability of containing the lost vessel. So based on this typo, okay, last known position, heading, time missing, and current, and so on. So what we're doing here, what that means. So here's a map right there. You see, and then we divide this one to, for example, 4 squares. Okay, and then we can figure out the trajectory of the lost vessel, right? This. Okay. So now then and then we collect the sample data for each square. Okay, then posterior what the the distribution of f, okay, can be expressed as what the joint probability distribution of x1 through xn and theta sample and theta divided by f of x1 through xn. What is this? That's the marginal probability, right? Keep in mind this. We have to consider theta too as a random variable. So this is going to be a marginal probability, which means that this what for if the theta is continuous random variable, then what? This is going to be integral, right, of the f, right, with respect to theta. Okay. So now the top one is what can be expressed as the what? See, product of the marginal probability, right, times f of theta. But actually, no, this is actually what uh the typo. There should be the bar and theta right there. Okay, here this typo. So now, but let's focus on the bottom one. What is this? Marginal distribution of x1 x. And I told you the marginal distribution of x1 x f x1 through xn can be expressed as we know that, right? Theta, a sigma of f of x1 through theta, or integral of f, right? Depending on whether or not theta is discrete or continuous. All right. So now here, DGR distribution. It means that here's we're gonna construct the what the formula of posterior distribution. It's gonna be equal to, I told you this right here, joint distribution of sample and parameter divided by the marginal distribution. That is equal to, yeah, I told you there is a typo, okay? It should be, there's the bar and theta it should be right there, okay? So it's typo, sorry. So Now then this is equal to f of x1 through xn bar theta, which is joint probability distribution of sample times prior distribution divided by, because we suppose that we know f of theta, okay, divided by what marginal distribution of the sample. Okay, so we define the Bayesian estimator theta as the value theta that corresponds to the mean of the posterior distribution f. Once you figure out the PDF of the posterior distribution, then we're gonna find the mean of that posterior distribution. That's gonna be Bayesian estimator. So, by the way, so here, okay, so in this, back to this example, so what is theta? What is theta? Theta is what? The location of the loss vessel, okay? Right. So now then, so here the posterior distribution is PDF of theta, and x1 through xn are constant. Yeah, so eventually x1 and xn, these are what? Observations in sample, right? Random sample. So sample data will be given, right? Specifically. Okay. So data is the random variable. Okay, see example. Bayesian estimator for the mean of a normal distribution. Let x1 through xn be a random sample from the normal distribution with the mean mu and the variance sigma square. Okay, so where mu and sigma square is unknown. All right. Assume that prior distribution for mu is normal with the mean mu 0 and the sigma 0 square. So I told you we in the Bayesian approach, we assume that prior distribution is normal. Okay. So now, so here the theta mu is theta. Okay. So here mu population mean. Okay. And then excuse me. So f of mu is equal to, this is prior distribution. Okay. 1 over, because since the prior distribution follow the normal distribution, right? So we can express the prior distribution of mu as like this. Okay. Now then what? That's other expression. Okay. So in the top one, I just expand the square perfect square. So we got this. Okay, and then I put the sigma square inside the square root. So we got sigma square. Okay. And then joint probability distribution of sample, which is f of x1 through xn bar mu. Okay, that is equal to, so yeah, well, how come? Because what? We got this. Why we got this sigma? By the way, so because this is what? F of x1 through xn bar mu is equal to f of x1 colon mu colon sigma times, understand that? So since the, give me a second, give me a second. So x1, xn be a random sample from the normal distribution. So for each, the sample data, follow the normal distribution. Okay. So this one can be expressed as the product of the PDF probability distribution, actually normal probability distribution, right? For each sample data. Okay. So now then, since each sample data follow normal distribution, so that each probability distribution can be expressed as like this. Okay. So we combining them, we're gonna get this. Okay. By the way, 1 over square root of 2 pi sigma, we're gonna multiply 1 over 2 square root of 2 pi times sigma, n times. So we're gonna get the 1 over square root of 2 pi sigma to the nth power. And then see the exponential term right there, exponential terms, combine them, which means that since all of these exponential terms have the same base, when you combine them, we're gonna get the sum of the exponent, which is this, e to the sigma of that fraction. Okay, so now then since the 1 over 2 sigma square is just constant, so we can bring it out of sigma. So we got this minus 1 over 2 sigma square and this. Okay, so now expanding the sigma terms, summation term, we got this. Okay, so thus the joint probability distribution of sample and mu is this. This is the joint probability distribution of sample and mu, can be expressed as what? Joint probability distribution of the sample times prior, probability, prior distribution of mu. So we plug in this one into what? Here, F, the joint probability distribution of the sample. And then we already got what? Joint, sorry, prior distribution, right? So we plug in the formula of the prior distribution into F of mu. Okay. All right. And then you got this. And then we need to simplify it, right? So we'll simplify, we're gonna get this. Yeah, love the algebraic expression, right? So please read this one carefully, okay? Follow this, then we're gonna get this one. U0 sigma square over n plus x bar sigma 0 square over sigma square over n plus sigma 0 square. Okay. So now here we can express joint probability distribution of sample and mu as follow. By the way, you see, give me a second. So right. Okay. So you see that here like this, dual mu times h2 a sub 2 and the x1 to xn sigma square mu 0. How come? Join the probability distribution of sample and mu, which is this, right? Which is what we got here. Join the probability distribution of the sample and mu, right? You see the F, this one. We got this one. It turns out that what this one was this. Okay, but as you can see that there is no mu. Mu is not involved. So it means that what? Joint probability distribution of sample and mu can be expressed as the what, a function depending on a sample sigma square mu 0, sigma 0 square, and then times a certain function of mu. Okay, so now let's see. So now prior distribution of mu, that's what we want to find out, right? This one is can be expressed as like this. Yeah, let's see. Okay, but see the top one. This is a joint probability distribution of sample and mu, right? This one could be expressed as what? G of mu times a function of x1, a sample and sigma square mu 0 and sigma 0 square. So we plug in this one in the right there. Okay, and then the top is what? Let's see this one. Give me a second. You see it right there. Top one. Oh, give me a second. Need. Oh yeah, so yeah, I found it here right there. So when you find out the joint probability distribution of sample and mu, so yeah, I know it's super complicated, right? But let me see. The key point is we wanna figure out. I mean, express this one as simple as much as we simple. Okay. So the right here, yeah. You see from here, which is the product of the joint probability distribution of the sample and prior distribution. That can be expressed as the e to the negative half times this one times a function of x sample data and then sigma square mu 0 sigma 0 square. And then, but what is this? Actually, this is this right there. Okay, it is this one here. So, and then upon completing the square in the exponent, this is the what second, yeah, join the probability distribution of the sample and mu, then it can be expressed as, so keep in mind is we're just simplifying this one, okay? Join the probability distribution of sample and mu, okay? Like this, right here. So we got this, e to d, right, this one, times h1, right? Now this one can be expressed as e to the, this one times h1, that is equal to, okay? Now see that the bracket, u square minus this one. So we want to make this one to the perfect square form. Okay, so the making this one the algebraic expression inside the bracket as perfect square form, we're gonna get this. mu minus that fraction is square, and then so the then what and then the what I think we get this sum of term from the h1. We have to take some term in h1, so h1 function will be um you know changed, I mean modified, I mean changed, right? So instead of h1 we got h2. Okay, right. So now then, see that this is the join the problem distribution of the sample and view. Okay, and then now we see that this one is a mean. Okay, and then that is the what is this is the sigma square. I mean the variance. We can see that. So in a joint probability distribution of sample and view, the mean is this, and then variance is this. Okay, and then see that mu zero, so right there, this one. Okay, so this is the mean. All right, so now then, so we express the f as a function of mu times h squared. You see that? This one on top right there. Which one? So sigma zero, I mean, give me a second. Yeah, top one can be expressed as the function of mu right there. Okay, it's function of mu, right? And then h2 can express that. So we know the dual mu, and the actually we can figure out h2, but it's complicated. So now, next one, and then see that posterior distribution of mu, we want to find out, right? So this one can be expressed as like this. So we already got top one, right? Okay, which is dual mu h2. Right? So now then, we don't have taken of the bottom one, okay? So the from dual mu times h2, we can get this one, e to the minus something, right? This one. I know comes from the dual mu, part of dual mu, right? And then the other one, the other part, we express the other part as h of 3, including the bottom one and then h2. Okay, so h3. Okay, so anyway, so why we just what is h3? Yeah, I'm not gonna figure out this one. It's too much complicated. Okay, so now then the this is recognized as a normal probability density function with a posterior mean. So now you see that here, this one times our function. Then look at this. This is the mean and this is the variance, right? Okay. So now then, so consequently, the base estimate of mu is weighted average of mu zero and x bar. For purpose of comparison, note that the MLE of mu and mu bar x bar. So see the give me a second. See, look at yeah. So you see the posterior mean right here. So in the MLE D1 in the what maximum likely estimator of mu was x bar, but Bayesian estimator we got deal with this. So it's a little bit weighted, right? So okay. Now suppose we have a sample of size n equals 10 from the normal distribution with unknown mean, mu, and variance 4. Assume that the posterior prior distribution mu is normal with the mu 0, 0 and the sigma 0, 1. If the sample mean is 0.75, sample mean, the base estimator of mu is this, 0.536. So the MLA estimate is 0.75, definitely. So 0.536 base estimator between prior mean and then MLE. Okay. So I know it's just too much complicated right there in the algebra, algebra, right? But you don't have to specifically figure out H1, H2, H3, the three functions. So, but the focus on the the exponential term, okay? And then you need to understand the all terminology in the Bayesian approach is prior distribution, and then joint probability, joint distribution of sample, joint distribution sample and parameters, and then posterior distributions. Okay. So next time I'll just look at the online problems. Okay. So let me stop here.